Okay, so we left off with our big Y of s being equal to s plus 4 over s plus 3 times s minus 2. And so once again, we're going to do partial fractions to divide this up into two smaller, simpler fractions. And because both factors are linear, we'll just take a constant over each one. Now, when we multiply it through by the LCD, we're going to have s plus 4 is equal to a times s minus 2 plus b times s plus 3. And then from here, again, we could either multiply out everything and combine like terms and then compare coefficients. Or when it's linear and simple like this, we can go ahead and just find smart values of s to substitute in and solve for a and b. So one such value would be s is equal to 2. In that case, the left-hand side becomes 6, and the right-hand side becomes 5 times b, and the a term cancels out. That makes b equal to 6 over 5. Another smart value of s to pick would be negative 3. In this case, negative 3 plus 4 on the left side makes positive 1. And then if we have a times the negative 3 minus 2, that's just negative 5 times a. So that makes a equal to negative 1/5. So our big Y of s then is a, which is negative 1/5 over top of 1 over s plus 3, plus the b, which is 6/5 times 1 over s minus 2. And now we can take the inverses of these two terms here, and you'll recognize that they're both exponential. So when we take the inverse, we end up with now little y of t equaling negative 1/5 e to the negative 3t plus 6/5 e to the positive 2t. And let's just kind of fix that little 5 down there. It kind of looks like an s, and that doesn't look very good. So again, that is going to be 6/5 for that second term there. All right. So that is our first example of why we're using this Laplace transform to solve equations. We take the Laplace transform on both sides, perform some algebra, and then take the inverse.